Okay, example 2. Steel bar that is 10 millimeter by 20 millimeter is subject to these loads up top here. So I think of this as multiple points on the same rod where there's collars that are either pushing or pulling at these different force values. Let's see, so my cross-sectional area was 20 millimeters by 10 millimeters. And then we have this loading condition. Right at one end it's pushing 20 kilonewtons. We have a collar pushing 28 that other way. Another collar 24 kilonewtons. And at the very end 32. And an interesting note is that in order for this rod to be static, all of these forces need to add up to, I'm missing a direction, 0. So the forces in the X need to be 0 in order for this to be holding still. Let's say 20 positive, 28 negative, negative 24, positive 32. Now that we're in strength of materials, I'm tempted to say most of it's static, but you don't necessarily have to have a static body. It could be like accelerating in one way, and then, well, it would just be flying through space faster and faster. But in this case, it's definitely static. So, 52. Yeah. So now we're going to look at the stress between two of these collars, like in the rod right there. So you're going to imagine a cut in the material. And so you have an end condition of 20 kilonewtons. So for this to be static still, you're going to need 20 kilonewtons in return. And so your stress at this section will be proportional to 20 kilonewtons. And I'm going to call this section A. I don't really know otherwise. So this is 10 millimeter, 20 millimeter. So got 20 kilonewton, 200 millimeter. Squared, because there's kilonewton millimeter squared. So what we got? And this is not the common unit. I want it in common units, so I want it to be Pascal if it's metric. And 1 Pascal is a Newton meter squared. So basically I want this top side in newtons and this bottom side in meters squared. So for every millimeter squared I need 1,000 squared. Per. Okay, I wrote this out wrong. So I don't usually do it this way. I just take the number I'm working with, kilonewton. 100 millimeters squared. And so I want to convert, so I need 1,000 squared millimeters for every meter. So it's like multiplying by 1,000,000. To get from millimeter to meter. So gives me, let's just do it. 10 divided by 100 squared. So that gives me 100,000. Still in kilonewton per meter squared. And to get to Newton meter square, I need another 1,000 to get rid of the kilo. So I'm gonna add 3 more zeros, geez. And now I'm in Newton meter squared, which is Pascal. And this looks like a big number, but when you're talking about stress, especially in steel, it gets pretty big. So megapascal is a pretty common unit. And so you'd get rid of, so 3 zeros is a kilo, 3 more, you get to mega right here. Just like in computing, you've got kilobytes, megabytes, gigabytes, terabytes. So it's the same stuff in computing. So that's one section. So now the next section includes the collar and the end force. And this collar force, 28 kilonewtons. And so at this break here, we need some force actually in this direction of 8 to keep it static. To keep the, it doesn't have to be static like I said, it's just that the net force needs to be the same. So the sum of forces in the x, whatever that net was previously. But it's a lot easier to be static. Which is 0. So this is positive 20 kilonewtons, negative 28 kilonewtons, and some unknown. So now in this section, so that'll be between this collar and the next collar, it's only experiencing 8 kilonewtons. Okay. So what was our area before? I kind of wrapped it up in this unit conversion mess. So it was 200 millimeters, and I want that to be in meters. So I'm going to take 200 divided by 1,000,000. To get to meters. Just want to make sure I get this right. Oh gosh. Huh. 3 zeros too. Okay. Which is why we end up with such large numbers for stress. I'm going to call this section B. So we had 8 kilonewtons divided by 3 zeros and a 2 meters. And that's going to be the same as a kilopascal. So again, I don't want to mess with that. So 40,000 kilopascal, 40 megapascal. And now that's why metric is strong. Let's go to the next one. So again, we're going to add up our two colors now. What's the next one? 24? 28? 20? Sum of forces. Unknown P. $32. Oh. Well, that's a good check. Our last force brings it back to 0, and it's 32. So you could have cut it from the other direction. It would have been easier. And all the while, you want to think about compression versus tension. So right here, 20 is reacted against with 20. That was our first problem. So that's in compression. Next, we have 28 and 8. So it's like 8 away from the break is now that's in tension suddenly. And now we've taken 24. Yeah, so this one's in tension out here. Because the arrows are away. Alright, so I don't know what section this is. See? 32 kilonewtons over 3 zeros and a 2. Jeez. Now we're at 16. 160. Which is pascals. And that is 92. Nope, there's more. I turned it off. Turning it back on. Because this is going to come up later. Now that we know what our stresses were. And actually, I don't even want to plot stresses. I want to plot load. So inside of the beam here, we had it split into different pieces. We said that there was a 32 load here, 20 load here, 8 load there. Where was that? So yeah, this side is in compression. Next one was 8 in tension. And 32 in tension. So I'm going to say just for plotting sake, that this is a negative 20 kilonewton load. And so you can think, so you could plot this all along the same axis, and then let's say this is 0. To represent as you travel along, we're going to say this is 32 kilonewtons high right here. This is 8 kilonewtons high, and this is negative 20 kilonewtons. So as you travel through the beam, first off, at one end, it's, I don't know, just ignore that for now. And then, so you cut right immediately to the right inside of the material. And from then on, it's negative 20 in reaction. So you don't have to cut like straight in the middle. You could cut quite close to the boundary. So it's negative 20 anywhere between this boundary condition and this boundary condition. And then it's 8 in between these two clamps, anywhere along it, you know, whether you get really close to the clamp or what. And then it's 32 between one clamp and the next end. And this is a, I don't know what to call this, a force diagram? Let's say it's a force diagram. And this will reoccur later, that we'll have force diagrams on beams. And it's really cool to, so like you were given a rod with different loads on it. And they're like this way. Is this right? No, yeah, this one was definitely this way. And these loads were, you know, 28, 24, 20. So you were given these loads. You found these internal loading inside of the beam. So these are the external loads. These are the internal reactions within the beam. And this is going to reoccur throughout strength of materials. All right, thanks.